Que é isso? Okay, everybody back. Let's continue. So now we are going to work with what we call a random forest, okay? Which is a collection of decision trees that we just saw, okay? And each decision tree, as I said, is trained on a subset of instances from the original set. That is what we call a bootstrap strategy, okay? So we go there in the original data set and randomly get some instances. And also, I can get instances with repetition. I can have repeated instances in my subset, okay? So each decision tree has an output, then the multiple outputs are used to decide the final prediction, okay? For example, using the majority voting schema, okay? So the idea, see, a large number of uncorrelated trees working as a committee can get better results than any single tree. And when I say uncorrelated trees, I can also say that they are uncorrelated and maybe weaker than a strong one unique decision tree, that combining weak classifiers, we can have a better result, okay, than having a unique classifier. So each of the uncorrelated trees are trained using a Bootstrap dataset. So a Bootstrap dataset is a dataset that is constructed randomly getting some instances from the original dataset, okay? Very nice. Okay, and the portion of instances that is left out of the Bootstrap sample is called out-of-bag sample, okay? So I have the original data set, I randomly get some instances, that's the Bootstrap data set. The instances that I didn't get are the out-of-bag sample. I can use this out-of-bag sample to evaluate the decision tree. Okay, nice. And, another characteristic is that each of the decision trees is constructed not only with a subset of instances, but also with a subset of the variables. So the Bootstrap dataset can be constructed using a subset of instances and a subset of variables. This guarantees that I have very different trees in my forest that combined make a stronger classifier. Okay, any doubts until now? Good. So to classify an instance, we do, for example, the majority voting in the case of classification. For regression, we can average the individual predictions. So we are going to have many decision trees, just like we saw before lunch, and the output of the forest will be the average of all the outputs of all the decision trees. Okay? And in the case of classification, a majority voting scheme. Okay? Problems? Nice. Okay. And remember, so the out-of-bag sample that I told you, okay, we can use the error in this out-of-bag sample to select features. For each tree, we calculate the error in the out-of-bag sample. Okay, this we call the error rate for classification or mean squared error for regression. And then we do the same again. We calculate the error, but after permuting each feature. So the difference between the two is then calculated and averaged over all trees. Then a feature is important if the difference is large between the original and the permuted sample. Okay, I'll try to do some drawing. Came off. Huh?
It's not showing the screen.
Okay.
Now.
Yeah, I'll try to do some drawing here. So for example, let's construct here a data set. Okay. So this is our original data set. I'll try to construct a bigger data set. Okay, this is sample 1, sample 2, sample n, okay? And this is variable 1, variable 2, variable 3, variable 4, and the target. Okay, so the Bootstrap sample will be a data set with a subset of the instances of the original data set. So let's say I get here sample 1, sample 3, I don't know, sample 5, sample 6, and sample 1, 2, 3, 4, 5, 6, 7, sample 8. Okay? So this is the out-of-bag sample. Okay? And let's see, let's suppose I get all the variables here. Or maybe only 3 variables and the target here. Okay? So sample 1 is part of my Bootstrap. I'll put a B here. Part of the Bootstrap. Sample 3 is part of the Bootstrap. Sample 5 is part of the Bootstrap. Sample 5 is part of the Bootstrap. Sample 6 is part of the Bootstrap. And sample 6, 7, 8, sample 8 is part of the Bootstrap. So here's sample 10. Okay? So all the other samples form the out-of-bag sample. So the out-of-bag sample. Okay, so here is the Bootstrap. Okay, and the out-of-bag sample will be sample 2, right? Sample 4, sample 7, sample 9, and 10. Okay, now let's suppose I induce, so this is out-of-bag sample. Out-of-bag sample. Now suppose I construct a decision tree, okay, and this decision tree has, I don't know, variable 2, then variable 3, let's say, variable 3, then here is a leaf 1, leaf 2, then it can be, I don't know, variable 1, leaf 3, leaf 4, okay? This is a decision tree constructed with the Bootstrap sample. And okay, suppose I'm going to have many bootstrap samples, okay? And correspondingly, many of these decision trees, right? Now what I'm going to do is to test this decision tree in the out of bag sample. Okay, I'm going to test the decision tree in the out of bag sample, and I'm going to get an error, okay, in the out of bag sample for the original data set out of bag. And I'm going to get this error here, okay? This error. Then what I'm going to do is that I'm going to get, for example, for variable 2, I'm going here in the out of bag sample, and I'm going to permute the values here, but only in this column, okay? Change here the positions of the variables, okay? For example, randomly. Change the position of the variables. Then I get the same tree and test here again, okay? And calculate the error in the out of bag sample, but changing the variable v2, for example. Okay, then what I'm going to do is that I'm going to see the difference between this error and this one. If the difference is big, that means that variable 2 is important for the tree, because I'm mixing the values and it is having a big impact in the performance of the tree. So if this difference is big, the variable is important. If the difference is very small, then that means that variable is not that important. So I'm going to do this for all the trees that have variable 2 in the forest. All the trees. So suppose I have 1,000 trees in the forest. I will perform this evaluation with all the trees that have variable 2 and average this error here. And that will give me the importance of the variable for the tree. And I'm going to do this for all variables in all the trees. And then I'm going to rank all the variables according to this importance measure. That's called the mean decrease in, I don't know, mean squared error or mean decrease in accuracy. Okay, I'm going to do this and use this measure as a ranking to evaluate the importance of the variable. Then I can do this with for many applications, including, for example, SNPs, ranking of SNPs according to a given outcome that I want. Okay, and on any kind of application you can think about.
This out-of-bag error would be the error that you get when you use this out-of-bag set as a test set for the... Okay, good. Yeah. Thank you.
Questions? Okay, so let's continue. Let me change here. Node off. Ah, very nice. Okay, so here I leave you with some useful links that you have already, right, in the material I sent you. And if you don't have any questions, we can go for the implementation. Good? Okay, so give me a moment. And here we are going to perform something very funny. Ooh, ooh, ooh. Okay. Let me just, is it okay for you to see in the slides? The size is okay? Okay. So as you can see here, I am going to read, okay, that SNPs data set. Okay, actually, no, I don't want to read this SNPs data set. I want to read this data set, right? Not with the dummy variables, because I don't need them. I can work with the original data set with categorical features. I don't have to work with the data set with dummy features, right? Here. And then I will go, I'll need to, again, do this. I'm just copying here, making a function to calculate here. I'm just copying here. I'm just copying the code of the preview class, okay? Yeah, and now I'm going to delete this because I don't need this. I don't need this, I don't need anything of this. And just to check if everything is okay. Yeah, good. So I just copied the code of the previous class because I want to work here with the categorical features, okay? Not with the dummy features. S and P, oh, head.
Ricardo, could you just show us again, please, which part of the code did you copy?
Yes. Yes. So this is this. I just changed this part. I'm reading the data snips and CSV, okay? And now I copy that function we have made that calculates the mode, remember? And then I just copy. You can copy just this part. That's the loop that I call when to apply the function to all the columns of a given row. Okay, I copied from the class before lunch. It's the same code we used before lunch. Is it okay? Good, good. Okay, now here I'm just seeing the data. Nice. I'm going to call this library that's called random forest. It's a very good, very used library in R, okay? And I am going to use this ggplot2 package because it's very used and we are going to need it to build some graphs, okay? Here, see, it's the number of executions, okay? The number of executions is how many times we are going to execute a random forest. Because it's important to perform many times the experiment for what I want to do. What I want to do, I want to rank, okay, the features in the forest to see what is the most important feature in the forest, okay, to make a rank. But only one execution is not enough, okay, because of the bootstrap procedure. The bootstrap procedure has a randomness in it. So it is important to perform the experiment many times in order to obtain many forests and then obtain many ranks and then see what are the most important features according to these many ranks. Okay, because every time I do a bootstrap data set, I obtain a different data set. So it's important to repeat the experiment many times. Okay. Usually I should perform like 1,000 experiments, but I'll perform here only 100 just for you to see. And here, number of important features is just a variable that I am using because I'm going to construct a ranking with 10 positions. Okay, I'm going to get the 10 most important features for every forest. So I'm going to set this variable here, non-important features equals to 10. Okay, and here, look at what we are going to do. We are going to use the percentage of increasing mean square error. Okay, that's what we are doing that. So the mean square error will increase if the variable is important. So we will use the percentage of increasing mean square mean square error to evaluate and choose the SNPs we want. So the more important SNPs will be associated with a high mean square error because of this procedure where we change the values of the feature and apply the decision tree again, okay? Okay, nice. So what I'm doing here is that I'm building a matrix, okay, with how many rows, okay? Number of executions, 100. And how many calls, number of important features, 10. Why? Because for each execution of the random forest, I will assign to a row here the 10 more important features. Then for the second execution, I will use this row here to store the 10 most important features, and so on until the row number 100. Okay? So there we have it. And now, I will use these structures here just to store the predictions. I am using a list, the true values in another list, and also the errors in a vector. Okay? Okay, why am I using a list here? Because the predictions is a vector, right? The predictions for each execution of the random forest is a vector, okay? With the prediction for every instance. So I'm going to store this in a list, because in a list I can store, I can have a list of vectors. Then I can index the list to get the predictions I want. Okay, so here. And now this is the main loop of the program. Look here. For all the executions, okay, for E varying to 1 until 100, okay, what we are going to do? I'm going to get the train data, the data, okay? It's not SNP data filter, it's just SNP data. SNP data, okay? SNP data, okay? SNP data and SNP data. So for every random forest, I will get my data set and split in train and test data sets. Okay? The same way we've been doing so far. And here, I'm going to induce a random forest. Okay? I'm passing the train without the label. Okay? That's why minus the number of columns of the data. And as target, I'm passing the target, X train target. And here I am inducing 100 trees. Okay, 100 trees. And this importance equals true tells the function that I want it to return the importance of the features according to the percentage increase of mean squared error. Okay, so we return a vector of, it will return to me the importance calculated for every feature. Okay, nice. After inducing the model, okay, I can get the importance of the features by using this command importance. This command is from the package random forest. So with this function importance, passing the random forest as argument, I can get the many values related to the importance of the features, okay? And here, because importance random forest features actually returns me a matrix. And the first column of this matrix returns me the importance of the features. Let's try to run the random forest just one time here in a separate window. So I'm going to do this. Okay, I'm set Y. No, I don't need the Y here. Okay, I'm just set here. I'm just separating train and test data. Okay. And now here I'm going to induce my random forest. Okay, random forest. Now I'm going to get the importance of the feature here. Importance, random F model. See, I get many things here. Whoa. So, see, this is the percentage increase in mean square error for every feature. Okay. And this is the increase of node purity. I mean, when using this feature, what's the increase in the purity of the node? Okay, according, for example, to the entropy. Okay, so what's interesting for me is this first column. Okay, percentage increase in mean square error. So what I'm going to do? I'm going to sort this first column. Okay, the importance to me is the first column. Here, the first column. So I have a vector where each position corresponds to a SNP. So what I'm going to do, I'm going to sort. This is my implementation, okay, but you can find maybe better implementations. I'm going to sort here the importance. I'm going to sort this vector, okay, in a decreasing order. See? Now I have the more important features according to the mean increase in mean square error. See? Okay. And I'm going to get the names. I'm going to get the names of these guys here. See? I got only the names of the vectors. Now I have the features that are more important according to the mean square error, decreasing mean square error. And remember that variable, no important features. So I'm going to get only the 10 most important features for this run. Is it okay up to now? Nice. Okay, after doing that, what I'm going to do? I'm going to make a prediction in the test data set, okay, to store the error, see predictions and true values. So I'm storing the predictions and the true values, and with this I can compute the error, the mean square error here, yeah. I can compute the mean square error associated to that run, okay? And see that these calculations here, okay, considering the out-of-bag sample and changing the order of the values of the feature, this was already performed, okay? Okay? When I got here the importance of the variables here, okay? The package performed these calculations for me using the out-of-bag sample. Okay, nice. So this loop here constructs to me, okay? Okay, and I forgot to tell you, né? The most important features, see, I'm going to store in this matrix here. So for the first execution, for execution number 3, for example, for the first execution, number 1, I'm going to store the most important features. So this is a matrix. See, everything is 0, but the first line here has the most important features for the first execution. So see, with 100 executions, I can take a look and see, for example, oh, I don't know, SNP 26 appeared, I don't know, 70 times as in the first position of the ranks. So now it seems it is very important, okay? And I can do a ranking with all the features. Okay, let's execute this. I think we'll take a little, maybe some time. Yeah, this will run for a little. Questions while this is running?
I guess kind of thematically to what is happening right now. Since there is like a performance cost to doing all these things, right? When do I choose doing something like this instead of just doing a decision tree from the get-go?
Instead of running one decision tree?
One decision tree, yeah. Like, is there a clear directive? Are single decision trees usually bad?
Well, there is a paper, very well established paper from the guy who proposed this random forest, Bremen, and he proved that using the random forests is much better than using one decision tree, okay? But of course, if you want interpretability, okay, you want to convert your tree in a set of rules, then it's better to use only one decision tree. Because you lose interpretability when you have a forest with 1,000 decision trees, okay? So you have to balance what you want with your application. Okay, you can compare the performance of the decision tree, one decision tree, with the performance of the random forest. Okay, doing an experiment with a decision tree in different splits of your data set, different training and test data sets. Okay, to have an average performance of only one decision tree and compare with the performance of the random forest. If you are interested in interpretability, then it's better to run only one decision tree. If you are more interested in finding more, be more sure what are the most important features of your data set, and is very concerned about not so much interpretability, but in performance in terms of accuracy, precision, then it's better to use a random forest. We have to balance things between one another. More questions?
For these simulations, you maintain it all the variables. Because you said that we can exclude some of the variables from some.
In the Bootstrap?
Yes.
Yeah, the package is doing it for me. Okay,
okay.
The Bootstrap he's performing, he's selecting, yeah, it finished running. He's selecting randomly some features and some instances.
He selects randomly.
But the package is doing it for me. I'm not performing it by hand.
Okay.
Okay. The package is calculating the decrease in mean squared error and everything. I'm just doing the ranking here.
Okay. And there's some reasoning behind selecting randomly the variables too for each tree?
Because you want very diverse trees, very different from each other.
Okay.
Okay, then to guarantee that you have very different features in the trees, it's better to have a subsample of the features as well, and not only the instances.
Okay.
More questions? Did you finish running? It finished for you too? Okay. Okay, now let's take a look at our variables here. So for example, predictions. No, predictions, okay, errors. Errors, see? I have a vector with 100 errors. Let's take a look in our variable here with the ranking of the features, right? See? So what we can see here is that most of the time we have it seems that feature 38 and sometimes 26 as the most important features. Okay? And then if we look at the second position of the ranking, then we have feature 26 appearing most of the times, and sometimes feature 38. Okay, so we can start concluding that, look, I run the algorithm many times, and every time I run the algorithm with different subsets of features and instances, SNP 38 was in most of the times the top feature in the ranking. Oh, there is a high evidence that this feature is important for the classification, okay, or for the regression, for my outcome. So what we are going to do now, okay? Okay. Let's count here how many times each SNP appeared in each of the 10 positions. So the first thing where I'm going to do here is transform this in a vector. Okay. When transforming this matrix in a vector, I'm going simply transform it in a vector. It's like every line in the matrix will be converted in a line and concatenated at all the lines, okay? And then with this function unique, I can obtain all the features that appeared in the ranking. So this already can be considered the most important features of my data set, because these are all the features that appeared in the 10 positions of the ranking. Actually, let's compare this with the multiple linear regression we did yesterday. Let me open here. Multiple linear.
I have a question. You have like 26 most important features. That's like half of the data set. Is that a coincidence?
Yeah, I don't know. No, I think it's a coincidence. Yeah, I could have, for example, I don't know, 1,000 features, then 50 more important, okay, that appeared in the data set. That's a coincidence. But let's compare here, for example, multiple linear regression. Multiple linear regression. Let's see here. I suppose I have here the most important features. They are saved here somewhere. No. Where's my lasso? No. Oh no, it's ridge and, sorry, I opened the wrong file. And it's ridge and lasso. Yeah, here. Okay, let's see if we have some of these features there in that data set. Okay, so SNP 18. No, SNP 18 is not here. But 21 is here, see? 26 is here. 33. No, 33 is not here. 37 is here. 38, what we saw that was the most important, is here. 42 is here. And 48 is here. So see, there is a big intersection between the features found by the ridge, the lasso, linear regression, and the random forest. Okay, there's a big intersection. So of course, every model has its bias. Every model will find different features. So at the end, we'll have to compare them. For example, we have a project that we are running different feature selection techniques, and then we are providing the biologists with the features we found that are more important. Look, the methods, all them together, for majority voting, they decided that these features here are very important. These SNPs, for example. Now you biologists have to validate this in lab. Okay, because of course you cannot trust in the machine. You can always have to have a validation in the lab. But using the machine learning, you can decrease a lot the work in the lab, because from 50 we now have 25. From 1,000, we have 50, to test. Okay, so let's continue here. So we have, of course, here 25. 25 important features, okay? Let's build a ranking. Look at what I'm going to do here. I'm going to make a ranking, okay? To make a graph, to make it more visible, the features that are more important. So I'll make a vector here that repeats these guys here, okay? Every position of the ranking, from rank 0 to rank 9, 10 positions. I'm going to repeat each one of these 10 times, okay? Okay, so this guy here, ranking per count per rank SNP C, I'm repeating these guys 100 times. Sorry. Each 10 times. Okay. Yeah, but there are more than 10 here. Why? C, happy. No, just a minute. SNP of unique is 10. Oh no, this is 25. Sorry, I'm getting it wrong. Yeah, sure. I'm confused with another variable. Okay, so I want to count how many times every one of the 25 variables appeared in the ranking. Okay, so I'm repeating each of these positions 25 times. Because now, see, what I'm going to do is that I'm going to count how many times, I don't know, SNP 38 appeared in the first position of the ranking. SNP, I don't know, here. SNP 9 appeared in the first position of the ranking. I'm going to make this counting. And here, SNPs, okay? I'm doing the same with the SNPs, see? I'm repeating these guys here 10 times, okay? Because now I'm going to put everything together here. What I'm going to do, look, for every position of the ranking, that's why, because 1 to 10, okay? Then for each SNP, I'm going to construct here what we call here, it's almost a regular expression. So for example, I'm going to search for this SNP, okay? I'm going to search for this SNP in this matrix to get how many times that SNP appears in the matrix. And I will put this counting here in this vector. Vector counts is this vector. Okay, I'm going to put this in this vector. This vector has 10 positions. So I'm getting a SNP. I'm searching it in a column of the matrix. So for example, I'm going to search this SNP here in the first column of this matrix, which corresponding to the first position of the ranking. And then I'm going to store here how many times that that SNP appeared in the ranking, in the first position of the ranking. And I'm going to do this for all the SNPs and all positions of the ranking. Okay? And in the end, I'm going to have this kind of data. You are going to see, let me execute here. You are going to have this. See? What I have here is that, see, for the first position of the ranking, okay, I counted how many times that SNP appeared in that position. So SNP 38 appeared 86 times in the first position of the ranking. SNP 26 appeared 14 times in the first position of the ranking, and all the other SNPs didn't appear in the first position of the ranking. Okay. Now if I get to the second position of the ranking, SNP 38 appeared 14 times, 26 84 times, 52 times, and all the other SNPs, they didn't appear. And so on. And as the positions of the ranking start to be higher, okay, as I go further in the ranking, more SNPs start to appear in that positions. Okay? If I go, for example, to the last position of the ranking, you see more SNPs appeared in the last position of the ranking. Okay, then I put some threshold here, for example. I can say, oh, I performed 100 executions, 1,000 executions, I know, 10,000 executions. The SNPs that appeared only, I don't know, 10 times in the ranking after 10,000 executions are not important. I'm going to cut them from the ranking. Okay, here, for example, I executed 100 experiments. So the SNPs that appeared, I don't know, less than 3 times in the ranking, I can cut them. Less than 10 times in the ranking, I can cut them because they appeared in less than 10% of the experiments. They were considered important in less than 10% of the experiments. Then I can cut them. Okay? That's the idea here of these experiments. And after doing this, I can perform a plot here. So I'm going to construct a graph with ggplot where I am providing this data ranking here. Okay. And this function here aggregates the things, okay? Aggregates the counting per ranking with the vet counts total. Counts per ranking post is this guy. And vet counts total is this one. So it aggregates this with this information to put things in a bar. So it will put everything that's related to R0 in a bar. Everything is related to R1 in another bar, okay? It will make a stack with the values in a bar, okay? So this function makes this aggregation here, okay? And it will aggregate in a bar graph here, right? And then I'm just putting labels like the position of the ranking, number of times it appears in the ranking, the importance of the feature, and the subtitle for the graph, increasing mean squared error. When I execute this, I have this plot. Okay, this plot tells me, of course, the colors here are not that good, but that tells me that SNP 38 is the one that most appeared in the first position of the ranking, R0. Then SNP 26 is another very important SNP because it appeared in the first position of the ranking, but also appeared a lot here in the second position of the ranking. Okay?
But what is the biological meaning of this graph?
No, there is, well, biological meaning. I'm only informing here what are the most important features for my biological problem. Okay, what are the most important SNPs found for my outcome? according to this algorithm. That's why I'm telling, okay? That's the only explanation. So think about a problem, for example, I'm going to use the rice example again. You have many SNPs for the rice, for a variety of rice. And at the end, you have as outcome the productivity of that rice, okay? So what I am telling is that, look, SNP 38 seems to be very important for the production of the rice. SNP 26 also seems to be very important, okay? All the other SNPs, okay, they may be important, but I'm not sure. Okay, according to the algorithm starts to have more doubt in these SNPs. But if you get SNP 38 and SNP 26, they seem to be very important. So now we have to analyze that in lab. Okay, make some experiments, I don't know. More questions? Okay.
So you did like a variable selection and looking for the SNPs that were more important. But what if you wanted to like what would be the procedure if we were focused more on constructing a good tree that we could like input new data and classify that data?
This can also be used to classify the data, okay? Because remember, here, every time I executed my, where's my experiment? Here. Every time I executed my experiment, I separated my data in training and test. So I'm looking for the best random forest that has the generalization ability to be a good forest in a test data set. Let's make some predictions here. Let's see. Okay, here. Oh, here I'm just performing some code to save the graph in PDF, okay? Save the predictions, the true values in a mode here that I can load then again using R, okay? But let's perform some predictions. So, separate training data here. Okay. So I'm doing the same thing again. Okay. Now what I'm going to do is that I'm going to, okay, run a random forest again. Actually, what I could have done is to save here the model, right? I didn't save the model, but I could have saved the model and tested all the models. But let's train a random forest again. Here, train importance, okay. Yes, it is training it. Now let's perform some predictions. Let's see if I remember how to perform some predictions. Pred, I think it's predict, right? Then I'm going to copy here from the new data. That's predict random forest model, new data, X test, but without GX test without the labels. Yes, I have some predictions here, Brad. Here are my predictions. Okay, now what I'm going to do is that I am going to evaluate, okay, I'm going to evaluate these guys here. Well, first I'm going to construct a tab where I'm going to do a cbind of the predictions and the true values. Target. Okay. Conames tab. Receives here. True. No, predictions. True. And I'm going to show the tab here. So I have the predictions and the true value. Predictions, true value. Okay. And now I'm going to calculate the mean square error. I'm just copy the code here. Here. The root mean square error. Okay. So I'm going to use the tab. Predictions true. So I'm going to do the following. Tab 2 minus tab 1. Any row tab. 174. And then the decision tree was 187. So if the random forest we obtained as smallest mean square error. But we lose interpretability.
To create that image selecting the SNPs, you did like 100 forests, right? Each one with 500.
No, 500 forests. 500 forests, and for each forest, it was 500 forests, but I executed, no, 500 forests, no, sorry, 100 forests,
yes.
Each forest with 500 trees.
But if, for example, if you wanted to do a prediction, would you be able to use this 100 forests with 500 trees each and do like a average over all of them? That would be possible or even advisable?
No, it can be possible. Yeah, you are going to have a forest of forests. Let's say that. Okay, you have a forest with many. No, you have like say, what's bigger than a forest?
A biome.
You have that biome with forests. Okay, but it's actually I didn't store here the models, but I could have stored the models here. And then perform 100 predictions using the 100 forests, and then average the predictions. I could have done that.
Okay.
Mm-hmm. More questions? No? Okay, if you don't have more questions, we can start doing a different thing. We can... Question.
Yeah. So this was random forest where the trees are independent.
Yeah.
But I know of another algorithm that has dependent trees. Could you maybe talk a little bit about that one?
Dependent trees?
It's the boosted regression tree one.
What's the name?
Boosted regression tree, BRT.
ERT?
T. Yeah, I know it's kind of the same thing, but the trees are dependent.
I think that boosted methods, they construct a classifier, then based on the errors of that classifier or that regression anyway, okay, they try to improve the predictions based on the errors of the previous classifier. So that's why they call it boosted. You boost the method. So you have many, for example, you can have 500 trees, okay? But every time you are constructing a trees, you also use the errors that were committed by the previous tree. And with this, you can boost the performance of this tree here. But I'm not very certain how it works as well. The mathematical calculations, I'm not familiar with that. But it uses the residuals of the previous tree and try to learn upon these residuals. And with this, you make a stronger classifier, boosted classifier, you know? Yeah. There is another classifier called XGBoost. That's very famous. And it is also based on this idea of boosting. Okay, that's improving the performance of one classifier upon the errors of a previous one. Yeah. More questions, guys?
I had a question that is, I understand that to do any of those, to use any of those algorithms, being the decision tree or the random forest, you need to have some pre-ordered clusters in your data. Some cluster that were predefined. Like you had a column that tells, oh, this is, I don't know, in the first that we had was green or red, V or F, and this type of thing. But here in the SNPs, we don't have this classification. So like, is importance to what? You know?
Yeah, but in this case, it was a regression tree.
Okay.
So you have the division that leads to a better real number outcome. Okay?
Okay.
So we have a division in our space, okay, that leads to a better prediction for a real value number. Actually, what the decision trees do, cam off. Yes. What a decision tree does is that it cuts our space only with hyper rectangles. Suppose you have here x1, okay, and x2 values. These are your variables, okay? These are variables. These are the nodes of the tree. So what a decision tree does is that, suppose you have, for example, let me think in a good example, I don't know. Here, and then here, and I don't know. I don't know here, for example. Okay. So how can you separate this data? So what a decision tree does is first, I'm doing an easy example here, okay? Is first to look, for example, in this feature, and then choose a best value here as a splitting point for this feature, and then cuts the space of features like this. Okay, then I go and look in the other feature. Then I find here the best split for the value of this feature. Then I cut the space like this. Okay, so the decision tree only makes this kind of splits in the space of features that we call hyper rectangles. Okay, in trying to improve what? To improve the separation between the values. The target can be numeric or categorical, but I am separating the values. Okay. So in our case, we have a numeric target. So it is expected that instances that with similar values for that target are in this space. Other instances with similar values for another target are in this space, and so on. You know? Now think about this in a multidimensional space. Okay.
Yeah, but like in the random forest, we are trying to find the most important feature, and it's most important to what, you know?
Most important to separate,
separate.
the data according to that target we are looking
Yeah.
for. The target is a numeric variable.
But is that just that I don't see in our data set what is the target, you know? But okay.
Oh, the target is that if you get your SNP data, I don't know, money. If you get your SNP
I don't have this.
data, no, it won't fit here. SNP data targets. Then you are going to have your target in your data. Okay? Is it okay? Okay? Is it clear now? Yes or no? I see doubts in your eyes.
Yeah. The target column wasn't in my data set, so I couldn't find it.
Okay. More questions?
Yeah, I think that it's weird because most of us are like used to working with like algorithms to find out stuff about our data. We don't have like the target or something that.
Ah, okay.
We're
So
trying
you
to-
work more with clustering, for example?
Yeah,
or-
exactly.
Oh,
Most of us do.
Nice, yeah. You know, the clustering, in my opinion, is a more difficult task, much more difficult task than prediction, than supervised learning. So in machine learning, this is supervised learning, okay? When you do clustering, then you don't have the target, then it's unsupervised learning. And then, in my opinion, it's much more challenging than supervised learning. But yeah. Okay? So, if you don't have any questions anymore, I would like to go further and show you another useful algorithm that we can use. Neural networks. Are you familiar with neural networks? Okay, so I'm going to show you from the beginning how we can implement a perceptron, okay? And then how we can use the model of the perceptron to construct more complex neural networks. Now I have to change here. Here, right? Okay. The year here is wrong. Nice. Okay. So let's continue. Yes. So let's talk about the perceptron. I think it's very good for you guys to know this because this model of neuron, not the perceptron, but the mathematical formulation of an artificial neuron is the basis, okay, for the modern neural networks using so far, okay, even for convolutional neural networks that are used for image classification. So this is very important, you know what's behind the things, to know what's happening, okay? So the perceptron was the first neural network written as an algorithm. We have an algorithm to train the hyperparameters of the artificial neuron, which we call the weights of the neuron, okay? So it was created here by Frank Rosenblatt. And look, the guy was from the psychology field, okay? And up to till now, engineers, physicists, mathematicians, okay, started to study neural network. And this model proposed in 1958 is still valid, okay? And it's the basis for modern neural networks. Okay. So in the simplest form, okay, this neural network is used to classify linearly separable patterns. Do you know what linear separable patterns are? No, this is not linear separable. No. Can you separate these three classes with one straight line? So no. So linearly separable patterns are the ones that you can separate with just one hyperplane. Okay? So a hyperplane in a space of 2 dimensions, okay, will be a line. A hyperplane in a space with 3 dimensions would be a plane, okay? So if you can separate with just one hyperplane, then okay, you have linearly separable patterns, okay? So the algorithm this guy developed was used to adjust what we call free hyperparameters of the model. So the weights of the model. So up to now, when we worked, for example, with the multiple linear regression, we were trying to adjust the beta values. Remember, those betas are the hyperparameters of the model. Here, the hyperparameters of the model are the weights associated with the artificial neuron. So every neural network, from the small ones until the more sophisticated ones for computer vision and so on, they have weights associated to the neurons. Okay, these weights are called the hyperparameters, free hyperparameters, and have to be adjusted with iterations in the data. Okay? So this guy, Rosenblatt, he proved that if the examples were linearly separable, the examples used to train the network were linearly separable, so the algorithm can converge and placing a hyperplane between the classes. Okay? Nice. So this is the model for an artificial neuron. This is called the Mcculloch-Pitts neuron model. Okay? So the model you have, you can think you have a linear combination of an input plus an input multiplied by a weight plus another input multiplied by weight plus another input multiplied by weight and so on, plus a bias. And then you get this linear combination and pass through a function, okay? That in this case here, we call, in the case of the perceptron, is a hard limiter. It can be, for example, the sine function. Okay? If this linear combination is a positive number, then the output is +1. If this linear combination is a negative number, then the output is -1. Okay? So this is a hard delimiter. So this is a simple model, and with this, we can classify data. Okay? We can do this. Now, hi.
What was the example you gave of a hard limiter? It has to be a function that saturates on both sides.
That's what? Sorry?
It has to be like a function of one parameter that saturates on both axes.
No, it's a function that simply gives the sign of a number.
Ah, just the sign.
Yeah.
Okay, I thought it was sign the trigonometric function.
No.
Okay.
So just a sign of a number.
Okay, thank you.
Okay, very, very simple. So for example, if I have my data spread like this, okay, suppose. These are linearly separable patterns because I can put a line here to separate the data, okay? So the objective, okay, of the algorithm, okay, is to draw a hyperplane, okay, that separates the patterns from the negative ones from the positive ones. So that's why the sign function. I get a linear combination and pass through this sign function. If V is below, if V is a negative number, then the output is -1. If V is a positive number, the output is +1. And this places a hyperplane in our data. Actually, we are going to see that with the hyperparameters that we are going to I forgot the word, to induce, né? We are going to find the values of the hyperparameters. We are going to draw a line, okay, that separates data. Oh. Okay. So see. So the Rosenblatt perceptron uses that model of neuron, uses this model of neuron. So the perceptron uses this model for the artificial neuron, okay? So for the neuron, what we have synaptic waves that are denoted by W, W1, W2, Wn. Okay, the inputs are denoted by X1, X2, and Xn. And we have a bias that's denoted by B. Okay, the function of the bias is to move the hyperplane in different directions. Okay. Having this, we can make the mathematical formulation of the perceptron. So we have the first thing to do is to compute a linear combination between the inputs, okay, and the weights associated to each input. So have in mind that X is a vector with n positions, okay, and W is a vector also with n positions. So we are multiplying two vectors position by position, okay? X1 times W1, X2 times W2, and so far. And adding a bias value, that's usually +1, okay? So the perceptron, so the objective is to classify the examples into two classes, positive and negative classes, okay? So an example represented by a set of features, we already know that, is classified in a class 1 if its output is +1, and in a class 2 if its output is -1. So there are two regions used to separated by a hyperplane. Two regions separated by a hyperplane, okay? So this gives to me a hyperplane, okay? This is a formulation of a hyperplane. So what we have here, we have a bias plus a linear combination. So this gives me a hyperplane that separates data. See? This gives me a hyperplane. That's exactly what I draw here. Okay, this is an illustration of a hyperplane, in this case a straight line, that makes a decision boundary for classifying problems in two classes. Okay? Given that the examples that belong to both classes are linearly separable. Nice? Okay. The synaptic weights, I mean the W's, are going to be adjusted in an iterative process using an algorithm that makes the perceptron to converge. Okay, we are going to see how this algorithm works.
Okay. Why is it equal to 0? W1, X1 plus W2, X2 plus bias equals to 0?
Because this defines to me a hyperplane. And I want that when I compare a new value to that hyperplane, I'm going to have a value that, a resulting value that's higher than 0 or lower than 0. So the value equals to 0 defines a hyperplane. Okay. see here. So here I'm putting more mathematical formulations. Okay. I'm putting in a more formal mathematical formulation. So the bias is treated as a weight associated to an input. So what I did here was to get that bias that was here. Where is my bias? Oh, this is not working. So I'm getting my bias here. I'm putting inside of the summation. Okay, I'm associating a W0, okay, with the bias, and setting the bias to a fixed value +1 or -1. That has only the function to move my hyperplane in space, okay? Yes, here. Now I have an input that's a vector, which is a combination of all my features, plus an extra input, okay? And my wage vector now is a vector composed of the wages, okay? Plus the wages that I'm going to adjust. Okay, so I just put the bias inside of the summation.
Yep. Question. What's T? Why is everything raised to the T?
Oh, it's this transpose of the vector.
Transpose.
Yeah, this is a transpose of the vector. Okay, now, so I'm treating the bias as just another wage and associating an input +1 to it. So, see, and putting this in a vector representation. So instead of, see, now, previously I had I from 1 to m. Now I have I from 0 to m, multiplying every input with a wage. And now instead of having this representation, I just put it in a vector form, okay? So I have a W transpose multiplied by an X, okay? And this gives me a number, okay? This number is almost the output of the neuron, okay? This is the activation function, the activation potential of the neuron. So this linear combination will be passed, will be given as input to the sign function that will give me +1 or -1. And so here. So equals 0 defines the separation hyperplane, the decision boundary, okay? This computation will be higher than 0 for all vectors that belong to class 1 and below or equal to 0, or most of the times only below 0, okay? For all the vectors that belong to class 2. So the idea is that I have a hyperplane that I find this hyperplane using many axes, okay? Many axes. Recall that in my Perceptron, I have only one vector of wages, only one. I have to adjust this only unique vector of wages. I have to adjust all these wages of only one vector using many instances of a training set. So I get a training instance, give to the Perceptron, get an output, and then using this output, we are going to see how we correct the wages of the Perceptron. Then we get another input, pass to the Perceptron, get the output, compute an error, use this error to adjust the wages. And we do this for many and many iterations using a big data set, okay? When we find the hyperplane, the good hyperplane, what we do? We expect that given a new value for x, if this x belongs to class 1, that I will call here positive, okay? That means that the computation of W, the adjusted W, with this new x will be higher than 0. If this new x belongs to class to the negative class, then the computation of the adjusted W with the x will result in a negative value. Okay? So that's the idea. Oh, okay. Okay, so let's take a look of this. So we are going to do this with many, many interactions, okay? So if the n as, okay, if the vector x in interaction n is classified by the vector w in the interaction n of the algorithm, then is correctly classified, then no correction is performed in the weight vector. Okay, so see, the weight vector in the next iteration will be the same weight vector if this calculation is higher than 0 and the instance belongs to class 1. O belongs to class 1. Hello, hello. Okay, belongs to class 1. And the value of the weight vector is equal to the same value, okay, in another interaction. If this calculation is below or equal to 0, and the x belongs to class 2, okay? On contrary, I'm going to adjust the wages. And how am I going to adjust the wages? With this formulation here. So if an instance is given as input to the perceptron, and the output of the perceptron is different from the true class of the instance, for example, it should be +1, but the true class is -1. It should have been -1, but the true class is +1. Then I have to perform this adjustment in the weight vector. So the weight vector in the next iteration will be the current weight vector minus a learning rate times the current input vector. Okay? So this is the learning rate that controls how much I'm going to adjust the wages of the perceptron. Okay? The higher this learning factor, the higher is the adjustment in the wages. The lower is the adjustment in the wages. So it controls how much I'm going to adjust the wages.
Question, and that's a parameter we passed to the function?
Yes,
Okay.
that's a given user parameter, given parameter. So, okay. So the objective of the perceptron is to minimize an error function, right? So for example, we want to minimize the mean square error. So we want to minimize an error function. Suppose that the surface of my error function is like this. I'm pretty sure you have seen this before any time, okay? So we want to find this. The objective is to find the global minimum, right? So the higher my learning rate, okay, that's used to adjust my wage vector, okay? The higher the value of the learning rate, the more is the adjustment that I will, the higher the adjustment in the vector of wages, right? And the higher this adjustment, the higher the jumps I give in the surface of the error. So I have more chances to jump, for example, the global minimum. Okay. On the other hand, if I use a value that's too low, then I will perform a very small adjustment here in the wages. Then I'm going to perform very, very little steps here in the surface of the error function. Then it can take like forever to reach the global minimum. So I have to find the good balance between the ideal. Finding the ideal learning rate is not an easy task. Okay, we have to perform different experiments in order to find the correct learning rate. For example, We can decrease the learning rate with time. So in the beginning, my wages are very wrong, okay? They give me a hyperplane that's very far from my data, completely wrong hyperplane. Then I can adjust the weights more faster. Okay, but with time, I decrease the amount of adjustment I apply in the weights because it is supposed that I am getting more close to the global minimum. Okay, it's not guaranteed that I will get the global minimum, but I can get the global minimum. I mean, in this case of the Perceptron, there is a guarantee that we are going to find the global minimum if our data is linearly separable. Then we are going to find it. In this case, it is guaranteed. Any questions? No? What time is it? Okay. Okay, nice. So we can continue tomorrow. Okay, seeing we are going to implement the Perceptron, and we are going to start seeing multi-layer perceptrons, and we are going home knowing how to use neural networks to classify data or to predict a real number of data. Okay? See you tomorrow.